I would like to start my talk with a personal opinion, and I would like to know your opinion as well. If perhaps I have forgotten something, please add it on the chat room, and perhaps we can discuss it right after my talk. So, some of the major applications of machine learning in computational chemistry that have been explored the past years are mainly related with the exploration of the chemical compound and material space. We heard many talks about this yesterday, and many groups are active on this direction, especially for drug discovery and new materials. A second application is the exploration of the molecular conformational space, mainly promoted by neural network potentials and similar approaches. But in my talk, I'm going to focus on a different exploration, in particular on the exploration of electronic configurational space. And electronic configurations are important first in order to understand different states, from the ground state to excited states of molecules and atoms and materials, but also in order to introduce the missing dynamical correlation from standard methods like Hartree-Fock. Usually Hartree-Fock is our first step. In Hartree-Fock, in restricted Hartree-Fock, we have a single determinant that is schematically shown here on the left-hand side of my slide. We have W-occupied spin orbitals, or W-occupied orbitals, and what we are doing, we are promoting electrons, one electron, like single promotions, two electrons, double promotions, and triple promotions. And if we have the full manifold of all these electron configurations, we can recover the full configuration interaction. So standard methodologies in order to explore this effectively, because full CI can only be applied on small molecules, include configuration interaction, perturbation theory, and coupled cluster. So in my talk, I'm going to focus mainly on coupled cluster, and at the very end, I will present a little bit about what we have done with multi-reference perturbation theory. So coupled cluster has been perhaps the main workhorse for accurate calculations the past 20, 30 years in our community. In particular, the coupled cluster singles and doubles with perturbative triples, the CCSD parentheses T, is now considered the gold standard of quantum chemistry. However, our gold standard has specific limitations. For example, we need very large basis sets in order to achieve the expected accuracy. And it also can be applied on relatively small systems. And in order to surpass these limitations, what we have done in the past, not me, but the community, is to introduce explicitly correlated schemes where we introduce terms that depend explicitly on the interelectronic distance of two electrons, the R12. These are the F12 methods of family of methods. Or we introduce base set extrapolations, with the most famous perhaps is the Helgaker two-point scheme. And there's also a large variety of different approaches, including pair natural orbitals, exploration of the locality of the electron promotions, fragmentation schemes, and high-performance computing. On this list, we would like to add also our data-driven methodologies that we and many others in this field have developed the past years. So let's go back to the coupled cluster ansatz. In coupled cluster, we have an exponential operator, our cluster operator, that is acting on a zeroth order Hamiltonian. This is typically the Hartree-Fock wave function, the zeroth order wave function. And the cluster operator includes one electron promotion operators, the T1, two electron promotion operators, T2, T3, and so on. For practical applications, we truncate this expansion, and in the most used truncated scheme, the coupled cluster singles and doubles, we truncate at the second order, and we exclude all the higher terms. So in the CCSD ansatz, we have an operator, the T1, which includes electron promotions from the occupied spin orbital I to the unoccupied spin orbital A. This is the standard second quantization formalism. And these are connected with a particular amplitude, the T1 amplitude that I'm calling here. The T1 amplitude can be considered as the weight that connects how important is this particular one electron promotion. Similarly, the T2 amplitude, the T2 operator, includes promotions of two electrons from IJ occupied spin orbitals to the unoccupied A and B, with a corresponding amplitude, the T2 amplitude. So in order to solve this problem, what we do, we form a set of projected equations where we compute the energy, which is now a function of the T1 and the T2 amplitudes, by using this project the equation with respect to the zeroth order Hamiltonian. And in order to obtain a set of linear equations, non-linear equations to solve, linear equations in order to solve, we need to project with respect to the first one electron promotion wave functions and the two electron promotion wave functions. So this process is solved iteratively, and after we converge this process, we have a new set of T1 and T2 amplitudes that give us the converged CCSD energy. The number of T1 amplitudes is relatively small. It's the number of occupied spin orbitals times the unoccupied spin orbitals, and n times O. And in most applications, in most implementations, this number is actually set to 0. The whole T1 amplitude set is set to 0. On the contrary, the T2 amplitudes are more important and they are more to compute. It's n squared times O squared, their number. And again, in most common implementations, we begin with them with a guess, which comes from a cheaper computational method, the second order perturbation theory, MP2. In MP2 theory, we have a product between the MP2 amplitudes that involves again electrons from occupied IJ orbitals to unoccupied AB spin orbitals times particular two electron integral. The T2 amplitudes of MP2 are also given here. And again, on my numerator, I have the two electron integral over the difference between the orbital energies for spin orbital I and J and AB. So at that point, we made a hypothesis a few years ago that we can use all this information that is included already on the two electron promotions from IJ to AB and extract a set of information features that we can use in order to map the T2 amplitudes from MP2 theory with the CCSD T2 amplitudes. In particular, what we did, we extract information for each spin orbital, IJ and AB. We obtain the energies and the one electron and two electron terms from that particular spin orbitals. So we form a vector, which we can introduce now to a machine learning algorithm in such a way that we can then later train and predict the amplitudes of the higher level CCSD method. This approach is different from what other people have done in the past. There have been many methods where we extract information from lower level theory, like Hartree-Fock and MP2, directly from the wave function of these methods. And with machine learning, we predict either the total energy or fractions, like the pair energies of the correlation energy from the CCSD. In our methodology that we call it loosely as DDCC, data-driven coupled cluster, we are encoding information from cheaper wave functions in order to learn more expensive wave functions, the parameterization of the most expensive wave functions. We have no dimensionality problems because we predict each amplitude separately. And once we have a predicted wave function, we can recover the full coupled cluster energy by introducing the predicted amplitudes into the standard coupled cluster solver. This will help us converge the coupled cluster equations faster. And this, since we have encoded the physical properties of the two electron promotions, we can hope for transferability. And with the examples that I have later, I hope I will convince you that we can achieve transferability with this scheme. Additionally, something we haven't explored yet, but we have considered, is that once we have a predicted wave function, we can either use it in order to obtain the energy or use the predicted wave function in order to obtain properties that are directly connected with that particular level of theory, like, for example, polarizabilities and whatever else we need. Our method, we have used for our method the Psi4 NumPy code. And in our feature space, we include all of these properties that I mentioned before. A few more are the 4 index integrals, the denominator of the MP2 amplitude, and especially the MP2 amplitude that we have already computed at a fast computational, with less computational effort. For testing purposes, we began with the k nearest neighbors. And since we knew that particular features have more importance than others, what we did at the very beginning was to use a small set of water molecules and introduce a hyperparameter on each feature. We trained this model. We optimize the values of these hyperparameters, and we do not touch this anymore. So we consider this as part of the model. So just to demonstrate what we can achieve with this scheme, we start with 50 water molecules, different conformers of water molecules, and we use 40 for training and the remaining 10 for testing of the model. And if I begin the calculation of these 10 water molecules with the MP2 amplitudes, I need to solve the iterative equations. Okay, the difference between the 0th iteration and the final iteration is, on average, is 6.5 millihartz for these 10 water molecules. So in other words, 6.5 is the distance that I have to cover in order to reach the convergence of the coupled cluster scheme. If, on the contrary, I will begin with the predicted amplitudes, then the difference between the 0th iteration and the final iteration is only 0.04 millihartz. So in other words, I have a prediction that gives me very close, energy to the exact coupled cluster energy. I can stop there and I can continue with that particular energy value, or I can reintroduce these amplitudes on my solver, my iterative solver. And if I do that, I have a speed up of about 50% with respect to the actual initial MP2 amplitudes. Also, the model behaves as we are expecting. It learns as it is exposed to more data. As you can see here, for 4 different basis sets, we have already reached very small, close to 0 errors with 40 molecules, or even with 20 for specific basis sets. And another demonstration of that the model actually learns the correct physics of the 2 electron promotions that they are included in our correlation energies. We have used 4 different conformations of 6 hexamers, water hexamers, the book conformation, the ring, the prism, and the cage. And again, if I will begin with the MP2 amplitudes, the difference between the 0th iteration and the final iteration is about 0.09 Hartree. Now, the correlation energy is more important, is larger here because I have more water molecules and more excitation, so it is significantly larger than having 1 water molecule. If I will build a model where I train it only with water monomers, as you can see, my error increases. It's almost a double. It goes close to 0.15 Hartree. The reason is that in this model, I have not introduced any information about promotions of electrons from 1 water molecule to another water molecule. So in other words, there is no information about the hydrogen bond network between the hexamers that I'm showing here. When we introduce data from water dimers, this error drops to 0.01. And if I introduce also data from trimers, this error goes to 0. So again, this shows that the model is able to learn accurately the physics or the chemistry, if you prefer, of the water clusters. And we show some similar behavior for larger clusters as well. So as a next step, we want to explore the locality of the 2 electron promotions. And this was more like an exercise for us. We started with, so far what we have tried was with canonical orbitals, which, as you can see, are completely delocalized. But if I will introduce a localized scheme, we can get beautiful orbitals which are between carbons, so 2 carbons for this linear alkane. For that exercise, what we did, we used the Nesbett theorem, which tells us that the total pair energy for each electron pair can give us the total correlation energy of this system. We play a little bit with the input features, and we train models by using small linear alkanes from propane till heptane. And as you can see here, without the localization scheme, we cannot use transferability in larger linear alkanes. But on the contrary, this is achieved, and this is a limit of 1 kcal per mole that we are showing here for larger alkanes from 8 till 18 carbon chains. A nice question that we got during the review process from an anonymous reviewer was if these models actually inherit the problems of MP2 or they behave as coupled clusters should behave. For that reason, we use a carbon dimer. And for the carbon dimer with MP2, as you can see, we get the wrong dissociation curve. It goes to very low energies at longer carbon-carbon distances. But on the contrary, the machine learning model does not inherit this behavior, but it follows more or less the same behavior as coupled cluster. In this case, you see all these inaccuracies only because we had a very small training set for demonstration purposes. A highlight from that study was that we were able to predict the energy of 133,000 organic molecules from the famous GDB9 database. We are using gradient tree boosting for this application. And as you can see here from our learning curves, with localization schemes, we're able with only 140 molecules, which are shown here, to achieve the accuracy that we were looking for, around 1 kcal per mole. So what now we are doing, and this is work that is done by my student Varuna, who presented this before in this symposium. We want to introduce localization and localization schemes inside our original data-driven coupled cluster scheme. And the idea is later to move also to parenthesis T and also to unrestricted coupled cluster. So for that purpose, we're moving our code from Psi4 NumPy to Psi4. And we obtain from Psi4 all the important features that we need in order to have our representation of the 2 electron excitations. We're introducing this in our machine learning model. And as I said before, we can either obtain the T2 amplitudes, the predicted T2 amplitudes, and calculate an alchemical coupled cluster energy, or introduce them back to the coupled cluster solver and obtain the exact non-alchemical coupled cluster energy. So with this new scheme, we have tried different small molecules, which are shown here. And as you can see, with canonical orbitals, again, we have large deviations. For the mixed model that was trained on all these 5 molecules, the errors are about 5 millihartry, while this error is dropped significantly when we introduce localization scheme. We have 10 times lower values from errors from the localized scheme. The mean absolute error is around 0.4 millihartry. Now, that was for k-nearest neighbors. Now we would like to do something more effective, more efficient. We're using XGBoost. The errors in this case are increasing, and the reason is that we have a very limited training space, training molecules. The errors are around 10 millihartry for the canonical orbitals, but again, we have a 10-fold increase in accuracy when we move to localized orbitals, and that actually gives us a lot of hope for the future. In terms of timing, k-nearest neighbors is actually way slower as we were expecting. That's why we would like to move away from this model. And apart from that, when we move to large databases, we don't want to compare every single instance with the whole data set. As you can see, that for the training of these models, we needed 35 minutes with the k-nearest neighbors and only 9 minutes with the XGBoost. And the same agreement, the same drop in timings is also for testing one molecule like the diethyl ether, which is here. The timings from XGBoost are actually very close to the MP2, so we can actually assume that we will have MP2 speed or close to MP2 speed for achieving the coupled cluster accuracy. Another scheme that we have explored in my group recently, this is work by my other student, Greer, who was presenting his work earlier as well, is to try the same, to use the same methodology, the data-driven methodology, for a method, a strongly correlated method like CASPD2. CASPD2 has been used extensively for transition metal chemistry, for dissociation of bonds, excited states. And the problems with CASPD2 is that we have to compute expensive 3 and 4 electron reduced density matrices, RDMs. We have an iterative solver again that we would like to surpass. And also the analytical gradients are non-trivial. Only recently we had the first implementations in the literature about the analytical gradients of CASPD2. What we tried in the beginning was to predict again the amplitudes, which are part of the first order wave function. Because if we know these amplitudes, again, we can calculate the CASPD2, the second order perturbation theory energy, correlation energy from them. However, right now we have abandoned this approach. We might revisit it in the future. What we are predicting right now is again the pair energies, the 2 electron promotions for all possible unoccupied orbitals, either active or virtual, for a given pair PQ. And with this scheme, we have tested it on a small molecule, perhaps the smallest multi-configurational molecule that is not diatomic, because we didn't want to limit ourselves on a diatomic, because we don't have enough virtual orbitals and diverse virtual orbitals for our training schemes. So we use Ozone, and we use also a significantly larger basis, active space, not the minimal 4,3, which is the typical active space for demonstration. So we use a larger basis set, active space, and two different basis sets, a double zeta and a triple zeta basis set. And we trained this model on the one-dimensional potential by playing with the angle theta of the ozone molecule. So by using 70% of the molecules for training and 30% for testing, we can recover the full potential for at the gas speed 2 level with this scheme. Here are the deviations between the predicted and the true during the training, and here are the predicted versus the true pair energies for the testing. As you can see, most of them are within a very small error from the exact. And if I sum all of them together, I can retrieve the full gas speed 2 energy. With the double zeta, as you can see, with only 60% of the molecules, we have achieved a 1 kcal per mole error for a total test, for a total correlation energy of 250 kcal per mole. And if I go to a triple zeta, the agreement is even better. And the reason is that I have more excitations to do, and this gives me more data to utilize for this scheme. So to summarize my talk, I have discussed with you our efforts to develop data-driven quantum chemical methods. The idea is to be able to do calculations on small molecules, small systems, obtain their information from their wave functions, the converged wave functions, in order to train machine learning models, and with these models to be able to do calculations on larger species. So in other words, we're trying to recycle the information that we obtain from the quantum chemical calculations. The idea is to use low-level wave functions in order to predict higher-level wave functions. We don't call this scheme as a delta ML scheme because we don't use actual energy, but we are using information from the wave function. So that's why we try to differentiate from the delta ML. We are able to encode reliably properties of the electron promotions, electron correlation, and we saw that with water clusters and linear alkanes. And currently we have a long list of topics that we would like to explore in the years to come. Before I finish my talk, I would like to briefly present to you a fingerprinting method that we have developed in my group, which goes back to the other two topics that I introduced in the very beginning, exploration of the chemical space and conformational space. We've developed a new technique that introduces topological information from functional groups of molecules. We're using persistence homology for that purpose. And here we have information about the atomistic type, but also about the connectivity between atoms. Here we have multiple points that they correspond to every atom pair. But in this area of this diagram, that we call persistence diagram, we have specific points that corresponds to different functional groups of a molecule. This point here corresponds to the phenyl group, and this point here corresponds to the methoxy carbon-carbon area. So actually, if we do this process for a large database, we can, and we have clustered where these points appear, and we can differentiate between planar phenyl groups versus non-planar, like cyclohexane points groups, which they appear constantly on different positions on these diagrams. Birth and death corresponds to the generation and the disappearance of the topological features of a molecule. So, since my time is over, I would like to thank at this point the people who have done the work all these years in the group. Currently, these methods are further developed by my students Greer and Varuna, who present their work earlier. All our machine learning methods have been initialized by Dr. Jacob Townsend, who graduated last year, and now he's continuing in industry as a data scientist. It actually breaks my heart that most of my students now are becoming more data scientists rather than quantum chemists, but that's a different topic to discuss. I would like to thank NSF for ample funding all these years, DOE and NIH for funding different projects. We have also collaboration with the Eastman Chemical Company. And of course, I would like to thank you for your attention.